Everybody, my name is Jean-Marc Morency. Today I'll be going to the pathway of the AAS.
Hi, my name is Kaylee Dax, and today I'm going to show you how to run the AAS.
And hi, my name is Victoria Regan, and I'm going to show you each part of the AAS and explain what each part does.
Atomic Absorption Spectrometer, or AAS, is an instrument used to analyze iron in samples. We have two different types of AAS, single beam AAS and double beam AAS. Each of them have different pathway, but with slightly differences. First, I'll go to the pathway of the single beam AAS. First, you have the source, which is the hollow cathode one. This source is specific to the metal that you're trying to detect. The source will emit a light that will travel then to the sample, which is located at the flame, where the sample is evaporated. Then, the light source heat up the monoparameter, which select a particular wavelength according to what the light from the source detects. The light is then reach the photomultiplier tube, which is the transistor. Take the particular wavelength from the Ebert monoparameter and convert the photon into an electric current. The electric current is then go to the amplifier, which will make it in a way that is readable by the computer. When this electricity is read out, the computer will generate a graph that will show the absorbance versus wavelength of the iron. Next, I will be talking about the double beam AAS. It's the same concept, but you have your source, which is the hollow cathode lamp, which is specific to the metal that we're trying to detect. But before you reach the flame, you have a part here called the chopper. The goal of the chopper is to let the wavelength either go to the flame directly or go to the monoparameter directly. So then the light goes to the flame, which is where you have your sample. The sample is evaporated, of course, and the light from the source detect that sample, which will then be converted into a particular wavelength by the Zerny-Turner monoparameter, which is different than the single beam AAS, which is the Ebert monoparameter. The light is then reach the photomultiplier tube. The goal of the photomultiplier tube is to convert the wavelength from the Zerny-Turner monoparameter into an electric current. The electric current will then go to the amplifier, which has the goal to make it readable by the computer system. The computer system will take that current from the amplifier and generate a graph that will show absorbance versus wavelength of that particular metal of the sample.
Now I'm going to take you through each part of the Perkin-Elmer A-Analyst 200 AAS, and I'll explain to you how each part works. In my hands, I have a silver element, HCl, which is a hollow cathode lamp. This lamp specifically is full of argon gas, but the lamp could either be full of neon or argon. So this one is full of argon, and the positive argon molecule, when you turn it on, is going to be accelerated toward the metal cathode, which you can see in here. It's made of whatever metal you want to observe, which I said in this case is Ag or silver. The positive argon molecule will collide with the metal cathode and causes the argon to neutralize, and hot metal gas will be released. The hot metal gas releases energy in the form of light, which is in the specific wavelength that you want to see. Next, I will show you the nebulizer, which you can find right in here. This is the nebulizer. This is the whole thing. This piece is used to atomize your sample and move free atoms along. You want free atoms because with this instrument, molecules are too large and ions are too small. So you specifically want atoms to observe. The nebulizer will draw up the sample through this capillary tube. We'll actually put this into your sample, and it'll draw it up through the tube into the nebulizer. The nebulizer will also bring in fuel and gas, and it will also remove through here anything that you don't want. It's basically the waste container, and this is the waste container below here. Next is the slotted burner, which you can see right here. It's this big gray piece. The slotted burner is where the atomized sample is actually observed. The atoms are drawn up into the slotted burner and are burned off to produce a flame. You will actually see a flame right here. It's important to take care of this part of the instrument because you can have carbonates, sulfates, and phosphates, which are really hard to dissolve, and they will actually form solids in the slotted burner, and they can prevent flame from actually coming through, which you don't want. This is Jean-Marc's drawing, which you saw earlier. This specifically right here is the monochrometer, which is inside the instrument, which I can't show you. The monochrometer is made up of one large spherical mirror, which will actually help focus the wavelength you want by actually like separating out the specific wavelength so it passes through to the rest of the instrument. The photomultiplier tube, which is the transducer right here, corresponds to this drawing right here. This is what's inside the instrument. The photons enter and hit these diodes. As they hit each diode, they form electrons, which multiply as they pass through. So one will hit here, and then you'll have 3, and then you'll have 12, and it'll just keep increasing. All of these electrons will form a current, and it's made bigger in the amplifier, so that a graph can be produced based on the electricity that is produced in the transducer.
Okay, so today I want to show you how to actually use the AAS. I'm going to run a demo here. Now first, one of the advantages of using an AAS is the fact that you can look at a mixture and you can look at one single element as if it's the only element present. Now today we have our copper lamp installed right here, so we're looking at copper in our unknown mixture of copper and nickel. Now first, we want to set our conditions. We're going to go to wavelength, and we want the wavelength set at 216.51. We're going to have our slit width be 1.8 nanometers, and that's all set. Okay, so we're all good here. We're going to press install lamp. And our current is 25 milliamps. It's good. Okay, so now we're going to go to flame. We're going to check our interlocks. Now everything looks good here. Now this instrument does not use this kind of pressure, so we don't need to worry about that. Now we're going to turn the flame on. And you know it's ready when you hear that little pop. And there it goes. Okay, now we're going to analyze. And first we're going to analyze our blank, which is just 1% nitric acid. We're going to take the capillary tube and set it in our blank. I'm going to press analyze blank. Okay, so we want to analyze our blank until this number here is 0. I'm going to do it again. Okay, so now our blank is at 0. I'm going to take the capillary tube out. I'm going to take our sample. And we're starting from the lowest concentration going to higher. We're going to put the capillary tube in the sample. And we're going to give it about a 3-second delay until the flame is ready. And then I'm going to press Analyze Sample. Okay, and this number here is its absorbance, and that took 1 second measurement. And it took 5 measurements, and this number is the average of the 5. Now we're going to take the capillary tube out. We're going to again analyze the blank before we run the next sample. Okay, we're going to press Analyze Blank, and this is going to go to 0 again. So now we have our next sample, which is at a higher concentration than our first one. We're going to again stick the capillary tube in. I'm going to give it about a 3-second delay. I'm going to press Analyze Sample. And again, this number is the average of the 5 measurements it took over the 1 second time period. And again, you would keep putting on the blank and then continue analyzing your samples until you were done, going from the lower to higher concentration. And then, when you're all done, you're going to turn off your flame. Okay, so we're going to turn off our gases. Now, before we shut off the instrument, we're going to bleed gas. Okay, now we're just going to turn off the power after we bled our gas. Alright, thanks for watching our demo today. Now remember, when you're trying to do this yourself, make sure that you know how to properly use the instrument. Make sure that you set the conditions, wavelength and the slit width, all those things that I showed you today to their proper conditions. Make sure when using that you also have a lot of solution. The AAS does use a lot of solution. And when you're done, make sure to always turn off the gases and always make sure to bleed the gases as I showed you. And thank you for watching, and I hope that you learned something.